So we're going to come up with, it looks like we're going to come up with three surfaces here, right? So we have a cylinder, X is not present in the cylinder, so it's just Y and Z. So on the Y, Z plane, you would have that circle, and then that would extend over to a cylinder. No, it's going along the Z. Oh, it's going along the X, so but it gets cut at X is equal to 0, and X plus Y, or X plus Y is equal to 10. So X plus Y is equal to 10. How's that going to look like? It's a plane, right? So I think it'll be a plane that's going to go up along the Z. So it's going to cut this. Wow, can you guys even see it? Yeah, it's a cylinder. So it should look something like this. It's a cylinder. You got the back plane over here. This is X is equal to 0. The front plane over here, X plus Y is equal to 10, and then the cylinder itself. S is the boundary of the region enclosed by the cylinder and the plane. So it'll have to be these three surfaces that we're dealing with. Okay? So let's, did anybody try working with those surfaces? Extra credit? No? Anyways, things like this would be interesting to try to draw with those programs. You can try to draw them and put them together, put these surfaces together. But drawing the surfaces individually is kind of tricky. All right, let's name these ones. Let's call this S1. S2, and S3. And so we're going to need to add up these three surface integrals together. Which means we need to parameterize them. So that's what we'll do. We'll parameterize them. We'll start with S1. We'll parameterize this using Y and Z. You can call it U and V if you want, but we'll call it Y and Z. And then X is going to be 0, so we know that we're going to have 0 in the X component. It's going to be 0 the whole time. Y is just going to be Y, and Z is going to be Z. And whenever you do a parameterization like this, it's always important to identify the region, the limits for your Y and Z, or for your independent variables. And instead of trying to find the equation of the circle and then saying it's from minus square root of this to square root of that, and we could just draw this because we'll assume that we're going to move over to some sort of polar coordinates. And I think this has a radius of 8. Okay. So we're going to want the magnitude of the magnitude of the cross product of the partial derivatives. Does the light bulb light up or explode? Okay. I'm not going to go through this whole thing because I'm seeing something in the function that's going to be important for us, and that is that x is equal to 0. So when x is equal to 0, your f is going to disappear anyways. But in general, you're going to want to figure this out, which we're not going to do. That's because once you figure this out, your integrand is going to be your f evaluated at r of yz, which is going to be x times z. Well, x is equal to 0. So it turns out that this whole thing is equal to 0. So when you multiply it by star, then your whole integral is going to be equal to 0, and then you're done. There's no contribution from this. Okay? So integral of S1 f ds. I put an arrow on top of that s, and there's not supposed to be one. Okay, so that part's done. Let's take a look at S2. I don't know if that's easier or the last one's easier, but let's take a look at S2. And we'll parameterize this. Now we have to parameterize the cylinder. And to parameterize a cylinder, I think it might be easier to use theta and x. Theta. So theta allows it to go around. I'm actually kind of mimicking cylinder coordinates, except that x is where it sweeps along. You know, we're used to having cylindrical coordinates as z is equal to z. You know, x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. But since the cylinder is going along the x-axis, your x is equal to x, and then your y will be the one with a cosine theta, and then your z is going to be the one with the sine theta. So that's what's going to happen, is that x is going to equal to x, and then your y is going to be r, which is, we have a fixed radius here as a cylinder. So that's 8 cosine theta, and then 8 sine theta. And one of our issues here is to try to figure out what our domain is. So our domain is going to require us to give limits for the two variables that we have. Yeah. Because it's going along the x-axis, and I'm kind of freely moving my x. Yeah, it's like cylindrical coordinates. Usually, I'm going to erase this, but usually we have x equals r cosine theta, y equals r sine theta, and z is equal to z. That's for these cylinders going straight up in the z. But since my cylinder is going along the x, I'm going to want this to be my x. So x is going to be the one that's constant. And then these two are going to move to the y and the z. Okay? So, erase all this stuff. My theta is going to go all the way around from 0 to 2 pi. That's what makes the cylindrical shape. My x is going to start with 0, but it stops at a certain, if I stop at a constant, then I'm looking at a regular flat cylinder, flat top cylinder. But my stopping point is at an angle over here. And so I have to stop at this equation where x is x and y is 8 cosine theta. So if I solve for x here, I'm going to go 10 minus y, and y in this case had changed to 8 cosine theta. All right, so I need I'm looking ahead and seeing what happens when I put x and z in there for the function, and it looks like there's nothing interesting that's going to happen, so I'm going to have to work this other stuff out. So I need to find out what r of x is and r of theta. And then I would need to cross it and find the magnitude. So with respect to x, I'm going to get 1, 0, 0. With respect to theta, I'm going to get 0, and then here I'll get actual values or actual expressions. Negative 8 sine theta, positive 8 cosine theta. So I want to cross it and then take the magnitude. So let's cross it first. And when we cross it, we're going to get another vector. So the first vector is 0, or the first component of the vector is 0, 0, 0 minus 0. A second component of the vector is 8 negative. It's the middle term is the j component's negative. And then I have 8 cosine theta minus 0. And then the last component is negative 8 sine theta minus 0. And then I want the magnitude of this. And if I square everything, I'm going to get 64 cosine squared theta plus 64 sine squared theta plus 0. And that's just the cosine squared and the sine squared. You would add them after you take out a 64, and then the square root of 64 is 8. All right, so this will be your ds with the x and the theta. And orientation doesn't matter here. We took the magnitude and because it's a surface integral and not a flux. So we don't need to worry about the orientation. So our integral is going to be integrating x times z dotted, or not dotted, but times ds. And then we have our limits set up over here, so we can just change this into our limits. This is going to equal to, I'm going to go with a theta integrating last, and then 0, 10 minus 8 cosine theta. We're integrating 64 times x times sine theta dx first, and then d theta. So I'm going to have x squared over 2, the integral with respect to x, but then I have to evaluate it, that weird thing, and then FOIL it all out to multiply by sine theta. So that just got a little too difficult for me. I'm going to use Wolfram alpha. Yeah. We can't take out the x because this is with respect to x, and we can't take out the sine x or sine theta because there's a theta in here. So constant limits are really nice. You can take stuff out, and then if you're adding or subtracting or multiplying, dividing, you can take things out. But in this case, we cannot separate this. So it's important to look at something and know when to be able to separate it and know when not to separate. All right, so let's call on Mr. Wolfram. I heard him talk. He gave a talk at Stanford, Stephen Wolfram, talking about Mathematica. So there's two of them. It's a double integral. And I'll just choose to do it all at once. I have a 64, which we should have brought outside, times x times sine theta. Just call it t. All right, so that's the integrand. The inner integral is our x values going from 0 to, I better put parentheses over here, 10 minus 8 times cosine t, and my outer integral is theta, or t, going from 0 to 2 pi. If you're comfortable with knowing how the graphs of sine squared, sine times cosine, cosine squared, sine and cosine, if you're going to go from 0 to 2 pi, that generally is a period. Uh-oh, that doesn't look good. What happened? It's dot dot. I need another parentheses somewhere. Where? After cosine t? Isn't it there already? Yeah. Anyways, yeah, if you're comfortable with the sines and cosines, and if you're integrating from 0 to 2 pi, usually when you take a look at one period of things, you know when things are 0. So this whole thing ends up being 0. Whoops. All right, we have 0 for the first one, 0 for this one. What do you think? You think we'll get 0 for the third one too? How did we parameterize the first one? We use y and z. So we can parameterize this the same way. We're going to use y and z also. But this time x is equal to, it's the front part of the plane, right? So the y and z are going to be the y and z. They're like the x and y if it was being, projected up. Z is equal to something. But this time it's x is equal to something. X is equal to that plane, 10 minus y. So this would be 10 minus y. And your domain would be the shadow that this thing would have on the yz plane. So it's essentially the same as the first parameterization. With the first parameterization, you're on x is equal to 0. Your second parameterization, you're on this other plane. But this is a shadow that you're going to have on your xy plane, on your yz plane. Yeah.
So why did you choose that combination right there? I know you could like some sort of variable and put it in there and make it in terms of two variables, but didn't we theoretically, if we were to just subtract the x on that one and put it in for the y component, would we get the same answer?
I don't think so. Because if you're letting x be a parameter and the x is moving a certain way, it might mess things up. All right, let's see what we're going to get out of this. It looks like we're going to have to do the f composed with r of yz, and that's f is x times z, right? X times z. So I have 10 minus y times z. That's my x and z. And so now I'm going to need to, it didn't all go to 0 like last time, so now I'm going to need to figure out what r sub y and r sub z are equal to, and then cross them. So with respect to y, I have negative 1, 1, 0. With respect to x, I'm going to get, or with respect to z, I have 0, 0, 1. So ry cross rz is going to be the cross product, 1 minus 0, negative 1, and then 0. Did I do that correctly? Cross product. So the magnitude is square root of 1 squared plus 1 squared. So that's just square root of 2. So this is going to be by ds. And so I have a double integral over this domain, d, 10 minus y, that whole thing times z times square root of 2 d dA. So this whole thing is the ds, and then so I'm just calling it dA. And so we can change this into polar coordinates with the y and z as the variables. So we'll let y equal to r cosine theta and z equal to r sine theta. And then your r limits are going to go from 0 to, this is 8. And your theta limits are going to go from 0 to 2 pi. All right, let's take the square root of 2 out. I'm going to say 10 minus r cosine theta times z, which is r sine theta. And the square root of 2 came out, and the dA becomes r. And if we integrate with respect to r first, that would be 0 to 8 for the inner integral, and then theta would be 0 to 2 pi. So let's put it in the Wolfram alpha again. So we have 10 minus r times cosine theta, close parentheses, times r sine theta times r. Okay, and so r is going to go from 0 to 8, and theta is going to go from 0 to pi. Zero again. It doesn't want to go down. All right, bunch of zeros. So if we put them all together, we got 0 for the first integral, 0 for the second integral, and 0 for the third integral. That just gives us 0. Okay? Yeah. Because it's 2, right? So before, I think you're talking about a line integral. So the line integral is the dot product with f with r prime.
And that's because of dimensionality, pretty much.
Right. Yeah. So now here we're talking about surfaces that requires parameterization with 2 variables, 2 parameters. All right. Let's put a 0 in and cross our fingers. Oh, you can't, because it's already overdue. The answer is 0. I looked it up. All right. So I think what would be good to start reviewing is to put the integrals all together in one space and then try to figure out what the little nuances are. And then take a look at all the different big theorems that all say the fundamental theorem of calculus. It kind of makes sense to do the integral first. Should we do that and kind of summarize everything? All right, let's try to summarize everything with integrals. So it's always good to start with, you know, your standard integral from Calc 1 and Calc 2. And this time, though, I'm going to write a little subscript I. And I'll trim the notation a little bit to try to mimic the other types of integrals that we're looking at. So this is your single integral. This is single or simple. Looks like a P. This is your single integral, and for us to make sense out of this, I'll do this in a different color. For us to make sense out of this, we want to figure out that I is an interval from A to B, and then you write your integral stretched out with limits from A to B of f of x dx. Next is we're looking now at a different geometry, geometric region D, and f is still a scalar function, and then this time we can't just integrate, since we're integrating with respect to two variables, we have to reassess how we write our differential dx, and so we call it dA to say that there's really two variables here. And we say dx dy or dy dx, and since we don't want to commit to the order of the x or y, then we split it up. And for this particular scenario, you're looking at a region on the xy plane D, where you have limits for x and y. And I'm just going to put a bunch of stars here. Oh, let me just put A and B here to make sure that we understand that the outer limits are always going to be constants. And so this double integral will have A and B for the outer limit constants. And then this could be constant, the stars could be constant, or it could be actual functions of y. And then you have f of x, y. dx dy. Depending on how you're setting up your area. So our third integral is over a solid with a volume element. And this is going to equal to, well, the volume element is something in 3 dimensions. And then we have to be able to describe this with 3 variables, x, y, and z. And in general, what we want is descriptions of the solid, and we always want our outer limits to be constant. So again, we're going to go A and B for our outer limits. Some functions for the y and z variables, and then you just put the x and the y and the z into the function. Okay, so this is all the stuff that we did back in chapter 15. And then once we got used to these integrals, we dove into some other stranger integrals. So the next type of integral is a path integral. This time your geometry is different because you're not doing an interval or some two-dimensional region or some three-dimensional region. You're doing a one-dimensional object in 2 or 3D. So this is a curve now. And because it's a curve, you have to follow how it moves around a specific length, arc length. And so that's where the description changes a little bit. So again, we can be in 2 or 3 dimensions. But your curve C is some sort of length here. And what we need to do is we need to parameterize C with some parameter t, one variable parameter, because it's a one-dimensional object. A curve is a one-dimensional object. And then we would have limits for this. So that we can change our integral into something that we can actually calculate by changing it back into a single integral. And what we're going to do is at each of these points on the curve, we're going to see what the function is equal to there. So that's a composition. And then at each of those points, we're going to multiply it by some small little arc length measurement. And so now it becomes a single integral that we should be able to do. And just to point out that this is your dr. This is a multiply, not a dot, because these are both scalars. Yeah, it's a multiply. And then our line integral is our first taste of integrating. These are all scalar functions so far. The little f's are all scalar functions so far. And now we get introduced to a vector field, and somebody says that we can actually integrate vector fields over some surfaces. And so when we do that, we need to kind of make a similar construction here where we're going to take a look at a curve, and then we're going to take a look at the infinitesimal number of dot products, an infinite number of dot products, where we're dotting the vector field at that point and some sort of direction that we're going. And so that's when we take a look at the actual tangent vector. So the same setup. We have C is going to be parameterized with R, and R is going to go, or T is going to go from A to B. And for each of these things, we're going to take a look at the vector field at a specific point. So the vector field might be going this way. And so at that specific point, the vector field is going one way, and then the directional the direction of the curve, the tangent vector, is going another way. And then finding the dot product between them is what you're interested in doing. And so here you can identify the differential of the actual vector dr. Yeah?
So the difference between a path and line integral is you're integrating over a vector function for the line integral and for a
correct. So remember that the book calls these two things line integrals, according to the book. But I'm making a distinction between the line integral and the path integral, just so you can tell the difference between the scalar function versus the vector field. Yeah?
And will you be calling it like, so like, do we get like solve the line integral or just have the scalar function?
I'll probably just say solve the integral.
Just solve the integral?
Yeah. And you have to figure out what kind of integral is it. Which one of these 7 possibilities. So the next integral is a surface integral, which extends our idea of a path integral to 2 dimensions. So instead of a one-dimensional curve that we're talking about, your surface now is a 2-dimensional object, and the dimensions will match the number of parameters that you have. So whether you call it u and v, or x and y, or y and z, or r and theta, or whatever it is you call it, those are going to be the parameters. Now, the thing about parameterizing with 2 variables is that parameterizing with 1 variable, it's kind of simple enough to be able to manage or imagine. But parameterizing 2 variables, what actually happens is that this thing, there's a special, the parameterization that you make is a special function that takes a domain in 2 dimensions on a UV plane and then makes it into a surface. So I think it was Evan's idea to think about this as like a rubber mat. You pull it, if your surface is a hemisphere, think about a flat rubber mat, and then that just push it down up along the surface of the hemisphere so that it just makes that rounded off shape. So this is a D in here. Let's just say D. So instead of calling it A to B, we can't do that anymore because it's 2-dimensional, so we have to refer to it as D, and then our problem then kind of snaps back to the 2-dimensional double integral. Yeah?
So can you say that the parameterization is collapses, so it collapses the
You could say it collapses, but you have to be careful. You could say it collapses down on the XY plane if that's how you parameterized it. So I think for this example over here, since this is y and z, this thing collapsed to the yz plane. And that kind of still makes sense. But now if you change the actual shape of it, this thing doesn't collapse. Your y and z are 8 cosine theta and 8 sine theta. It doesn't collapse to the xz plane anymore. It collapses to an x theta plane that's not in our picture. It's somewhere else. And so that's why when I try to draw this, I try to draw this not on the xy plane over here like we've done in the past, but it's somewhere else in some other UV plane that's bringing those values in to make that surface. So imagine this is the rubber sheet that you're going to take, and then you're going to wrap it around the surface in 3 dimensions. So this one, we'll just change this one into a double integral and default to the double integral and how to solve for that. But Now, once we find out what our parameterization with a domain, we're going to be able to be able to look at this as a double integral now, and then do whatever rules that we have learned from the double integral. So the dA is going to be du, dv, or dv, du, depending on the order. And then depending on the domain, you'll integrate it the way you need to integrate it. And we also learned a couple of things back here. Back in Calc 1 and Calc 2, we learned about U substitutions and trig substitutions. So over here, we learned about polar coordinates. And over here, we learned about cylindrical and spherical coordinates. So if for some reason we're calculating those integrals, we might need to change or make our substitutions. And then our last one is the flux. Now this one has two looks, two forms. One form, the first form, seems like a natural progression from the path, line, surface, and flux integrals. But sometimes you might be able to take advantage of the shape of the surface and the normal vector and change the flux integral into a surface integral. So notice that this is actually a surface integral. Because when you dot two vectors, you get a scalar. Now you have a scalar, and this ds doesn't have an arrow on top, so it must be a surface integral. But anyways, depending on how you approach this, you may look at it as this f.ds with arrows on top. And so the f part is the vector field evaluated at the parameterization, and the ds part will include your parameterization. And again, the dA is like a du, dv in whatever convenient order you're working it out. Okay, yeah. Yeah. Okay. I do want to make one more comment about the ds, the ds without the arrow on top. So I'll do that on another page. Yeah, so let me do this ds. And let's talk about the ds. Yeah, I don't know if you've noticed, but most of our parameterizations most of the parameterizations we use is called the graph parameterization. So in other words, if your surface S is a surface that looks like this, and it's the surface that could be expressed as z is equal to some function of x and y. And I'll use g because we tend to use f to be the integrand. Then we can actually parameterize this by saying r of xy where x is x, y is y, and then z is equal to g of xy. And so the ds, if you remember, it's the magnitude of r x cross ry, or r whatever cross r whatever, ru cross rv. So whether you call this x's and y's like I'm doing, or u's and v's, we can find the magnitude of the cross product by finding the partials. So depending on how you cross them, I think if I cross it this way, Rx first, it'll be negative Gx, negative Gy, positive 1. And we didn't talk about orientation, but for the vector fields, orientation will be important. But anyways, the magnitude of this is where I want to get at. Well, it's part of the gradient, gx squared plus gy squared plus 1. It's that surface area formula that we saw early on in our class. And since this is really the most common parameterization for a surface, for surfaces that would fit this parameterization, it turns out that this is going to be really, really important for us. Or it has been, right? It has been important. We've been calculating this. I don't know if you knew it or not, but we have been calculating this a lot. Yeah?
So we could say that the magnitude of the partial derivative of whichever variable, in this case x and y, that's the surface area?
Yeah. So it's actually called the surface integral because, remember, if f, the scalar function's f, if that was equal to 1, then this is really just the surface area formula. So little f's over here, all the little f's in all these integrals, by the way, you can set them equal to 1 and you'll see some measurement of geometry, whether you're looking for a length of an interval, an area of a D, a volume of E, an arc length of C, or the surface area of S. If f is equal to 1, then they all become just geometry problems. It's what? Was that a joke?
Yeah.
I want to hear a joke.
Normal unit vector is just a unitized version
Of this. Yeah. And then the ds will cover the other part.
What I'm saying is that could you just then ds as a vector is just the gradient with the dA added?
ds as a vector is a gradient. Well, it's not really the gradient, right? Because there's a negative 1 there.
I can use theoretical to be there.
Well, it's not. You have to be careful about, if you throw that negative 1 in there, it's officially not a gradient. It would be a gradient of a different type of function.
What I'm saying is that if
All right, we'll do that later, Evan. This is one of the pages in your section 1610 that talks about the fundamental theorem of calculus and the types of integrals. It kind of touches a little bit of the type of integral that you have. The fundamental theorem of calculus back in the old days is the derivative. The integral of a derivative of a function is equal to the original function evaluated at the endpoints. All right, so that's the first integral, the first fundamental theorem of calculus. Now, if I just reword that, we can say the integral of derivative of f is, it's like evaluating at the endpoints is like one less integral. But I won't say that for now. I'll just say is the original function, func, at the boundaries. Because that's what's happening is you're taking a look at the endpoints. The endpoints are essentially boundaries of your limits. Now, if you follow that thought process through, the fundamental theorem of line integrals says that if you're taking an integral of a derivative, in this case a derivative is a gradient, then that's equal to the original function evaluated at the boundaries again. Start and end point. Now, if you go to a double integral, if you're taking a double integral of this derivative-looking term, and it is in fact a derivative-looking term, it is in fact the curl of something, which is a derivative of a vector field, then this is equal to the original function, which is a vector field, evaluated at the boundary. Now, it's not just evaluated at the boundary, but you have to put it through a line integral. So you can say it's from a double integral to a single integral. Although the single integral is a line integral, it still goes down one integral less. And if you follow that thought process through with the Greens or Stokes, you have a surface integral, or this is actually a flux integral, a flux of a curl. So integral of a derivative of a vector field, the curl is a derivative. Integral of a derivative of a vector field is equal to the original vector field evaluated at the boundary. Except you can't just evaluate at the boundary, you have to actually do a line integral for that. And then finally, the triple integral of a derivative that's a div of a vector field is equal to one less integral, so that's a surface integral, it's actually a flux integral, of the original vector field. So this is a derivative of f, this is f by itself, and it's one less integral evaluated at the boundary. In this case, E is a solid, the boundary of a solid is a surface, a closed surface that encompasses that solid. Okay? So this was quick rundown of all the big theorems, and it's really all just the fundamental theorem of calculus. And next time we'll do a bunch of problems from taking advantage of these big theorems. All right? Okay, start studying now. Start working on those integrals and start practicing. Take a look at those quizzes. You guys have copies of the last couple of quizzes and worksheets that we worked on? I'm not. Yeah, we're going to go. You guys are going to have one problem from each of the first two exams. So your final exam will be one problem from the first exam, one problem from the second exam, and 4 or 5 problems from Chapter 16.